Namaste. Today we are going to discuss about the weak viscous interaction, right? So the weak interaction we already know from the flow over a flat plate. We have considered one is strong interaction and another one is weak interaction, right? So here we will consider the weak viscous interaction. We already know by definition of weak viscous interaction, there are various physical effects, right? So the first one is the rate of growth of the boundary layer is moderate, and we had a discussion on d del star by dx is reasonably small. And again, because of this rate of boundary layer growth is moderate, the outer inviscid flow is only weakly affected, right? So if it is so, then the feedback is also negligible. That we had a discussion sometimes back. Now we will have a further discussion, right? So I acknowledge John D. Anderson's hypersonic and high temperature gas dynamics, right? So this is what we had a discussion, right? The you have a strong interaction region and you have a weak interaction region. And for a weak and strong interaction region, the properties and the chi bar, which we had a discussion in the last class. Now, today we will discuss about the weak interaction where the d del star by dx is moderate in this region, right? Anyway, and we already know that the feedback is also very much limited or very small, or at times we don't consider there is a feedback, right? Now, let us start with the weak interaction characteristics. Say the first point which we need to discuss is d del star by dx, that is moderate, right? So if it is moderate, let us assume, say, let us assume d del star by dx is so small, right? Because we know that this slope d del star by dx should be very small, right? Hence, we can consider the k is equal to m infinity into d del star by dx, which is less than 1. And hence, if we consider k square, which is very much less than 1, right? So we already know the pressure equation, right? Say P by P infinity is equal to 1 plus gamma into gamma plus 1 by 4 k square plus gamma k square into root of gamma plus 1 by 4 square plus 1 by k square. So our consideration is if k square is very much less than 1, then we can write the pressure equation Pe by P infinity, that is equal to 1 plus, here you will have the gamma k, so gamma k plus this gamma into gamma plus 1 by 4 k square. So this is the pressure equation, and by a larger approximation, we can say that the PE by P infinity, which is approximately equal to 1. Right? Now, we already have an equation for del star. So, let us write the equation del star, that is proportional to x by root of Reynolds number into m infinity square into root c. So let us write d del star by dx, that is proportional to root of mu infinity by rho infinity v infinity. You will have a x here, right? So I take this x out and finally write the equation. So m infinity square into root c, and you have one x here, right? So it will become x power minus 1 by 2. Right? So by this way we can write this equation as that is equal to m infinity square by root of Reynolds number into root c. Right? So we have equation for d del star by dx. Here we need to understand one particular point, because you have you should have remembered the equation where in the strong interaction we have considered the feedback, right? Feedback from the inviscid region. But here there is no feedback, right? No feedback, right? No feedback of changes in the inviscid flow in the boundary layer, right? So we know that here there is a feedback, right? So here, since the d del star by dx is moderate, you have no feedback. So by that way, we can write the equation now, say del star, which is proportional to x power 1 by 2, and d del star by dx is proportional to x power minus 1 by 2. Right? Here you see, here you have x and rho vd by x and this x. So finally it is like a del star is proportional to x power 1 by 2, and d del star here it is proportional to x power minus 1 by 2. Now let us write the equation here, k, right? Because we already know k is m infinity into tau, m infinity into theta, m1, theta 1, and finally we can write this also, m infinity into d del star by dx, right? So this is proportional to, I can write m infinity q by root of Reynolds number by substituting the previous version of d del star by dx. We can write into root c. So this is again chi bar, right? So we can say that for strong interaction in the previous class, right? For strong interaction, we can write k is proportional to chi bar square, I mean k square is proportional to chi bar. For weak interaction, k is proportional to chi bar. So by this way, finally we can write the equation for weak interaction, PE by P infinity, that is equal to 1 plus B1 into chi bar plus B2 into chi bar square. right? So by having the assumption that K is small enough, we can write PE by P infinity, that is equal to 1 plus B1 into chi bar, right? So the point here is that the chi bar is the governing parameter that dictates the induced pressure increment for the hypersonic viscous interaction, right? So in both the cases, right, even in the strong interaction also, we had the similar equation, right? And now there is, one of the pioneer in hypersonic flow, Hayes and Hayes and Probstein. What they have done is they have considered the gamma is equal to 1.4 and have derived the relation for the pressure ratio for an insulated flat plate, right? Say I will write for insulated flat plate, um, insulated flat plate for strong interaction. We can write PE by P infinity is equal to 0.514 chi bar plus 0.759, right? This is their result. And similarly for weak interaction, they have arrived to P by P infinity, that is equal to 1 plus 0.31 chi bar plus 0.05 chi bar square, right? So in all the cases, we can understand that for the case of strong interaction, our chi bar is greater than 3 for strong interaction, and chi bar is less than 3 for weak interaction, right? So let us see some of the results what the previous researchers has done, and say the pressure ratio P by P infinity, right? Here P by P infinity, and the chi bar they have considered here. So you can say that, see the value for the strong interaction cases has been given here, right? With the various methods they have considered, right? So see, this is by Bertram and the Kendall and like that, and they consider the Mach number also for various Reynolds number. And we can finally say that for a weak interaction and for a strong interaction, they have arrived, right? And the equation P by P infinity is also from this graph only by considering gamma is equal to 1.4, right? So this is what the conclusion we have, and finally we can say that for strong interaction, the chi bar value is greater than 3, and for weak interaction, it is less than 3, right? And in all our discussion, we have assumed that the viscous interaction has a laminar boundary layer, right? So if we consider a turbulent boundary layer, then for strong interaction and weak interaction, we may need to have the different solution, right? So with that particular note, I stop the weak interaction characteristics, right? So thank you very much.